So basic two-box situation here. We've got an 83 kilogram box on a table or a surface. We've got a 45 kilogram box hanging off the edge of the pulley. We're going to just do something really simple. We're just going to find out the acceleration of the system, and we're going to say, keep things nice and simple. We're going to say there's no friction right now, and we're just going to find out what the acceleration of the system is. Now, first of all, let's see what was trying to move this thing. Now, the only thing that is trying to move the system is the 45 kilogram box. If we cut the rope, it would fall. The 83 kilogram box would do absolutely nothing, so it's not really pulling. So the 45 kilogram box is the only thing that's actually pulling, and of course it is pulling with its force of gravity. So if we do the mg for this box, we have about 440 newtons of gravity pulling on it. So that is the only applied force there is, and there's nothing else trying to slow it down. So not only is that the applied force, it'd also be our net force. So to find the acceleration, that's just net force divided by mass. 45 kilogram pink box is the only thing pulling, so we got 440 newtons trying to move it. There's nothing slowing it down, so that's it. And then we divide by the mass. We'd want to use the total mass altogether of the two boxes, so that would be 128 kilograms. So if we divide the two out, we get the 440-ish, we get the 128. It'd be accelerating at about 3.4 meters per second squared, and that is it. Alright, so let's see if we can change the situation a little bit. Let's say it is in dynamic equilibrium. So of course, equilibrium, that means that there is no acceleration. Okay, so the net force is zero, there's no acceleration. And of course, this means that it is moving. So this is moving, so it's moving this way, but it's not accelerating. So there's also static equilibrium, which means it would be at rest and not moving. But this one is moving at a constant speed, not accelerating. So that means we must have something slowing it down. And the only thing that would, of course, slow it down would be some friction. So now we've incorporated some friction up here with the top box. So let's see if we can find the coefficient of friction that would allow us to have dynamic equilibrium. Alright, well, let's see. How much is trying to move the box? Well, there is 440 newtons. That doesn't change. The 440 is trying to move it. Well, if there's 440 trying to move the system, and the net force is zero, so there's no acceleration, that tells me the force of friction must also be 440 newtons, or negative 440 or 440 in the opposite direction. So there must be 440 newtons of friction between that box and the tabletop. Alright, well, to find the coefficient of friction, that is the force of friction divided by the normal force. Now the normal force has nothing to do with the 45 kilogram box because it's not where the friction is, it's not even sitting on anything. The normal force would just be the weight of this box because that is where the normal force is coming from. So if we do the 800 or 830 times 9.81 to find the weight of this box, so the mg for that box is about 814 newtons, that is what is supplying the pressure of the normal force between the two surfaces. Alright, so let's sort of piece things together. For coefficient, I need the friction. Well, I figure out the friction has to be 440 newtons. The normal force has to be 814 newtons, so I just have to divide those two out. So 440 divided by 814 is going to give me a coefficient of about 0.54. And remember, there's no units for coefficient of friction, it's just a ratio of the forces. So what actually happens is the units actually cancel out. So a coefficient of friction of 0.54 would allow this thing to be in dynamic equilibrium, not accelerating, still moving, but not accelerating. Any higher coefficient at all, this thing would not be moving at all. And any less of a coefficient of friction, it would move, but it would also accelerate. Not accelerate at 3.4, because that's with no friction, but somewhere between 0 and